Let us consider the case of R load. We just have a single resistor at the output of the rectifier. On the left side we have the half-wave rectifier circuit with resistive load and the corresponding waveforms of VO output voltage, IS source current and VD1 in the half-wave rectifier circuit are shown here. Now on the right side we have both possibilities of full wave rectifier shown, and in the full wave rectifier with center tap transformer and 2 diodes, we represent the diodes in red color, and in the 4 diode rectifier we represent diodes in blue color, so the numbering is again from D1 to D4. As discussed earlier, in the 2 diode rectifier, 2 diode full wave rectifier, the diode D1 will be conducting in the positive half cycle and the diode D2 will be conducting in the negative half cycle. When D1 conducts, output voltage VO is equal to Vs times N2 by N1. So here the waveforms are shown for N2 is equal to N1 because they will be identical to the waveforms of 4 diode rectifier when the number of turns N2, half of the number of turns of secondary winding, is equal to the number of turns of primary. So when D1 is on in the positive half cycle, output voltage is equal to Vs, and when D2 is on in the negative half cycle, output voltage is equal to minus Vs. The voltage itself is negative, so the output voltage becomes positive, which is shown in red color waveform in the first plot. And what are the diodes conducting in the case of 4 diode rectifier? In the case of 4 diode rectifier, D1, D2 will be conducting in the positive half and D3, D4 will be conducting in the negative half. But the voltage is again VO is equal to Vs in the positive half and VO is equal to minus Vs in the negative half. So we have the same waveform here. And what is the average value of output voltage? The average output voltage is 1 by pi integral 0 to pi Vm sin omega t, because the periodicity has reduced to pi, and this integral will give us 2 Vm by pi. How does the current flow in the positive half cycle? The positive half cycle, in the case of 2 diode rectifier, current flows like this, and in the case of 4 diode rectifier or bridge rectifier, current flows through D1 and D2 and comes back to the source like this. So the source current Is is equal to IO in the positive half cycle as shown. And how does IO vary? IO is simply VO by R. R is the value of the output resistance, load resistance shown here. And in the negative half cycle, current flows through D2 in the case of 2 diode rectifier and closes its path as shown. And in the case of 4 diode rectifier, current flows through D3 and D4 as shown here. So in the negative half cycle, Is is equal to minus IO as per the definitions that we have given, because now the current is entering the positive terminal of source. The current leaving the positive terminal of source has been defined as positive direction for Is, so it will be negative in the negative half cycle, and that is what is shown here. Same is true even in the case of 2 diode rectifier, that is with the center tap transformer, because in the negative half cycle current is entering the dotted terminal as shown here, and in the positive half current was leaving the dotted terminal on the secondary side. So the input current will become sinusoidal as shown in the second waveform on the right side in green color. And what is the difference between these two full wave rectifiers? The difference lies in voltage across the diode. Voltage seen by the diode when it is off. So the voltage across diode in 2 diode rectifier is denoted as VD1A, and the voltage across diode in 4 diode or bridge rectifier is denoted as VD1B, and they are shown plotted here, VD1A and VD1B. Of course, when D1 is on, the voltage across D1 is 0, since we are assuming ideal diodes for analysis, and same is the case with D1 and D2 for bridge rectifier. But when D1 is off in the negative half cycle, what is the voltage seen by diode D1 in the center tapped transformer rectifier? It is the sum of the voltages across these two windings. In fact, the full secondary winding voltage will be experienced by diode, because when D2 is on, this point is connected to this point. So the full secondary winding voltage, which is double the input voltage, since we are considering N2 is equal to N1, double the input voltage is seen by VD1. And in the case of 4 diode rectifier or bridge rectifier, when D1 is off, D3 is on, so this point is same as this point, and VD1B is simply Vs, the input voltage, and that is how we can show the difference between 2 diode rectifier and 4 diode rectifiers. So the maximum voltage that appears across a diode, which is VRRM, repetitive reverse maximum voltage, or another term that is used for this is peak inverse voltage, PIV, is minus Vm in the case of a bridge rectifier, while it is minus 2 Vm in the case of a 2 diode rectifier. Another difference between the two full wave rectifiers is that in the on state condition, 2 diodes are appearing in the current path. In the case of a bridge rectifier, the current flows through the source, D1, load, D2 and back. So 2 diodes are appearing in the path. That means the voltage drop across 2 diodes appears in reality, whereas in the case of a center tapped transformer rectifier with 2 diodes, there is only one diode drop that comes, either D1 conducts or D2 conducts. So this becomes more important when we deal with lower voltages. For example, you want to build a 5 volt DC supply, one would go for a center tapped 2 diode rectifier, because the diode drop, typical diode drop of 0.5 volts or 0.8 volts is very significant when we compare with 5 volts. However, the circuit becomes bulky because of the transformer involved. So apart from these two differences, one is the voltage across diode when it is off, and 2 diode drop or 1 diode drop in the on state. Both circuits are identical in terms of output voltage and input current. Both the 2 diode and 4 diode full wave rectifiers are identical in terms of output voltage and input current waveforms.